Very good morning to all. I am Dr.V.Gopinath, Kungunadu College of Engineering and Technology, Tiruchirappalli. Today we are going to see steady flow energy equations from the subject of engineering thermodynamics. The steady flow energy equations, it comes in engineering thermodynamics for a UG BE mechanical engineering students. So this is a steady flow energy equation means the rate at which the fluid flow through a machine or any system will be remains constant. So that means the mass flow rate throughout the system will be constant, and in this diagram we can see that which will have the system, which will have the inlet and the exit. The inlet, the datum will be Z1 and the pressure will be P1 and area is A1, and the exit, the datum will be Z2, area is A2 and pressure is P2. The fluid velocities are inlet is C1 and the exit will be C2. It will be surrounded by the boundaries. So as we know that the total energy entering to the system is potential energy plus kinetic energy plus flow energy plus internal energy plus heat. So your potential energy will be mgh, but here we are considering as h will be datum, that is z, and the throughout the system mass is constant, so that the potential energy we are taking as g z1, and the kinetic energy is half mv square, so that here that c1 square by 2 plus the flow energy will be the pressure plus the specific volume, so that P1 V1 plus U1 is internal energy plus Q is heat transfer. The total energy leaving is potential energy plus kinetic energy plus flow energy plus internal energy plus the work extracted from the system, so that G is Z2 plus C2 square by 2 plus P2 V2 plus U2 plus W. So this is that energy entering to your system and energy leaving to the system. So according to the first law of thermodynamics, the total energy entering, which is equal to total energy leaving. So here the entering will be G Z1 plus E1 square by 2 plus P1 V1 plus U1 plus Q equal to Z Z2 plus C2 square by 2 plus P2 V2 plus U2 plus W. So in this, enthalpy is H equal to U plus PV, and we can substitute that P1 V1 plus U1 equal to H1 and P2 V2 plus U2 equal to H2. So the steady flow energy equation will be G Z1 plus C1 square by 2 plus H1 plus Q equal to Z Z2 plus C2 square by 2 plus H2 plus W. So above equation, the mass flow rate throughout the system is constant, so that we are not considering the mass flow rate here. If in case the value of QW in kilojoule per kg, if they are given in the problem, then the enthalpy H1 H2 also in kilojoule per kg, then the formula you have to rearrange it. So G Z1 by 1000 plus C1 square by 2000 plus H1 plus Q equal to G Z2 by 1000 plus C2 square by 2000 plus H2 plus W. Similarly, if the Q value and W are given in kilowatt and the H1 and H2 are in kilojoule per kg, in that case we have to take out the Q value from the mass flow rate and W value from the mass flow rate. So the formula will be M into G Z1 by 1000 plus C1 square by 2000 plus H1 plus Q equal to M into G Z2 by 1000 plus C2 square by 2000 plus H2 plus W. In a steady flow, the rate of mass flow rate throughout the system is constant, so that mass flow rate M equal to area into velocity divided by the specific volume. So according to the continuity of mass equation, M equal to A1 C1 by V1 equal to A2 C2 by V2. Here the throughout the system mass is constant. Next one, the application of steady flow energy equation to various equipments. First one, we are going to see about the boiler or steam generator. So this we are mainly focusing on the power plant components. So the first one is boiler. So boiler is the main function is to conversion of water into the steam with the help of heat energy. So in this you can see that the boiler will be kept in a same datum height, so that Z1 equal to Z2, and the velocity throughout the boiler will be constant, so C1 equal to C2. So in the boiler we are going to supply the heat energy, so the work will be 0 here. So that steady flow energy equation will be rewritable H1 plus Q equal to H2. So from that Q equal to H2 minus H1. Similarly, for your condenser, the condenser is heat extractor, so that means the steam will be converted into condensate with the help of the cooling water. So here same thing, the condenser will be kept in the same datum height, so the Z1 and Z2 are same, and the velocity throughout the condenser is constant, so that C1 equal to C2, and condenser is a heat exchanging component, so we are going to calculate the Q value, so that the W will be 0 here. So the formula for your steady flow energy equation of the condenser is H1 plus Q equal to H2, so that Q equal to H2 minus H1. So in this case your Q value will become minus value. The next one is the turbine. So turbine is conversion of potential energy into mechanical energy, and it is the expansion process. The high pressure steam enters to the turbine. When it's leaving the turbine, it will be the low pressure. During the expansion process, we are extracting the work output. So the heat transfer will be 0, and the turbine is kept in the same datum, so that Z1 equal to Z2, and the velocity throughout the turbine is constant, so that C1 equal to C2. So steady flow energy equation for the turbine will be W equal to H1 minus H2. So here the W value you will get in kilojoule per kg. If you want to convert it into kilowatt, means you have to multiply it with mass. The next one will be the nozzle. The nozzle is a device which will increase the velocity of the kinetic energy of the working medium. So nozzle normally it's classified into three things. One is conversion, next one is diversion, next one conversion divergence. So in this case we are going to calculate the exit velocity. So nozzle will be kept in the same datum height, so that Z1 equal to Z2, and the nozzle it will only the fact of velocity, so work and the heat transfer will be 0. So the steady flow energy equation, when we are substituting that, we will get that C2 equal to root of 2000 into H1 minus H2 plus C1 square. So these are the four components which will be the steady flow energy equation formula for the thermal equipments. The next one we are going to see about the problem on your steady flow energy equation, which will be the combination of heat exchanger, turbine and nozzle. So we are going to apply those steady flow formula in this problem. The question will be air at a temperature of 15 degrees centigrade. So inlet air temperature is 15 degrees, so the T1 equal to 15 degrees centigrade. So we are converted into the Kelvin. We have to add 273, which is passes through a heat exchanger. So the air is passes through the heat exchanger at a velocity of 30 meter per second, so that the C1 value is given as 30 meter per second. The temperature is raised to 800. After the heat exchanger, the T2 value will be 800 degrees centigrade, and it enters a turbine with the same velocity, so that the velocity which is leaving the heat exchanger and which is entering to the turbine, both are same, so that the C2 equal to 30 meter per second, and expand until the temperature falls to 650. So after the expansion, the temperature is falls to 650, so that your T3 will be 650 degrees centigrade. We are converting into Kelvin plus 273, so you will get the 923 Kelvin. And leaving the turbine, air is taken a velocity of 60 meter per second. When the air leaving the turbine, the velocity is 60 meter per second, so that C3 equal to 60 meter per second to the nozzle, and the temperature falls to 500 degrees centigrade. After the nozzle, the temperature is 500, so that T4 equal to 500 degrees centigrade. We have to add plus 273, you will get the 723 Kelvin. If the air flow rate is 2 kg per second, so mass flow rate is given as m equal to 2 kg per second. Calculate the first one, rate of heat transfer in the heat exchanger. The heat exchanger value you have to calculate the Q value. The second one, we have to calculate the power output from the turbine. So the turbine work value we have to calculate W. The third one is velocity at exit from the nozzle. So nozzle exit velocity we have to calculate, so that is the C4. So in this diagram you can see the process 1 to 2 is heat exchanger, the inlet air temperature is given and the exit temperature also given, inlet velocity is given and the exit velocity also given. The process 2 to 3 is turbine, the turbine inlet temperature, exit temperature, inlet velocity, exit velocity are given. So from that we are going to calculate the W value. The process 3 to 4 is the nozzle, so T3, T4, C3 is given. So from that nozzle we are going to calculate the C4 value. So the first process 1 to 2 is heat exchanger. Apply the steady flow energy equation. The formula is m into g z1 by 1000 plus c1 square by 2000 plus h1 plus q12, which is equal to m into g z2 by 1000 plus c2 square by 2000 plus h3 plus w12. Here the datum is not mentioned here, so that we have to consider the z1 equal to z2 and the velocity is c1 equal to c2. Here both are the same 30 meter per second, 30 meter per second, and the work done is not given in the problem. It is a heat exchanger. We are going to calculate the q value. So that q1 to 2 will be m into h2 minus h1 is the final formula. So that h we can represent as enthalpy equal to cp into t. So that m into cp into t2 minus t1. So you can substitute the cp value of the air is 1.005 and T2 value is, we know T1 is given in the problem and the M also given. So from that we can calculate the Q value is 1577.85 kilowatt. Similarly for the process 2 to 3 is the turbine. We have to rewrite the formula. This is 2 to 3. So that M into G is Z2 by 1000 plus C2 square by 2000 plus H2 plus Q2 to 3, which is equal to M into G Z3 by 1000 plus C3 square by 2000 plus H3 plus W2 to 3. So first one is heat exchanger. We have to write the formula for 1 and 2. Inlet, the entering will be 1 and leaving will be 2. Here the process 2 to 3 is entering will be 2 and leaving will be 3. So here the Z values are not given, so that we have to consider the Z2 equal to Z3. And this is the turbine process, though heat transfer will be 0. And they are not mentioned any heat losses or heat absorbed in this problem. So we have to calculate the W value. C2 is given as 30 meter per second and C3 is 60 meter per second. So we have to substitute that mass is 2. C2 value we know, H2 you can represent as Cp into T2 and H3 you can write it as Cp into T3. So all this value we know, Cp value is 1.005 for air. From that we can calculate the W value. 2 to 3 is 298.8 kilowatt. For the process 3 to 4 is nozzle. So we have to write the steady flow energy equation. 3 to 4, inlet will be 3, exit will be 4. So the formula is m into g z3 by 1000 plus c3 square by 2000 plus h3 plus q3 to 4, which is equal to m into g z4 by 1000 plus c4 square by 2000 plus h4 plus w3 to 4. So this is the nozzle. The heat and work transfer will be 0 and the nozzle is kept in the same datum height, so that z3 equal to z4. So we have to, the h3 will be cp into t3 and your h4 equal to cp into T4. So substitute the mass value, velocity value, temperature and Cp value. From that we can find out the C4 value. C4 value will be 552.36 meter per second. So this is that steady flow energy equations and basic formulas and the derivations and how to apply the steady flow energy equation in the applications. Thank you.